Hey everybody, welcome back. We're going to talk about measures of variation next. It's the next section in chapter 3, which is 3.3. And I have conveniently created another data set for you. And let me just sort of plant a seed here. Let's say that I've got a class of 15. So n equals 15. And I'm going to try and determine what's going on with these guys. So I go around to each person in the class and I ask them how many siblings they have. All right, now I totally made this up, and I, of course, listed it in perfect order so that we could have all sorts of fun with it. And I say, how many siblings do you have? And they let me know. So we've got 2 kids that are only children. We've got 6 kids that have 1 other sibling. We have 4 kids that have 2 other siblings. There are 2 kids with 3 other siblings, so there are 4 kids in the family. And then, oh, sweet goodness, we got 1 kid who's got 7 siblings. The jokes write themselves. You can write them yourselves. So it's pretty easy if we wanted to play around with the measures of center, if we wanted to play around with mode. Mode's easy to see. Let's see the mode. That's a freebie. Let's grab that one straight off the bat. The mode of this guy is 1. The median, and let's see, I want to find the value where there's 7 values below and 7 values above. You can count either from the top or the bottom. Remember, we got n equals 15. So 1, 2, 3, 4, 5, 6, 7. It appears to me that the median is that 1 right there. The median is also 1. And then the mean, if I plug this data into my fancy schmancy little calculator, I don't want to do that in my head if I don't have to. What do I call this? L3. Then I throw it in, and my mean is 1.8. Now, notice the mean got sucked over to this outlier. This number 7 here appears to be an outlier. So this kid's got 7 siblings, is pulling the mean to it. Okay? Now, those are all measures of center, but what we want to talk about today is we want to talk about measures of variation, or in this lesson, excuse me. In other words, how much does the data vary? If we got rid of 7, if we were to cover up 7, we would say, oh, not very much. You know, all the values are between 0 and 3. That's not very huge, but you throw that 7 in there and all hell breaks loose. The most rudimentary measure of variation is called the range. Oops. It's called the range. My pencil's getting a little crazy today. And that's always real simple. That's just the highest value minus the lowest value. All right, which in this case appears to be 7 minus 0, which is 7. All right, that tells us the entire, that's the distance, as it were, from the lowest value to the highest value. Now, that may be a little bit counterintuitive to the way that we would explain range. If somebody says, well, what's the range of data? You may say, well, they range from 0 to 7. But in statistical nomenclature, we say that the range is 7. Now, that can get a little tricky if we don't have the data sitting right in front of us. Now, let's actually go through an exercise just for fun. And let's make a histogram here. Now, let's see how badly I can draw this thing. Oh, yeah, this is going to be a bad one. You know what? Gosh, I think I need to take an art class or like a drafting class. That's what I need. And there's not a straight edge on this tablet, so it sort of screws me up. All right, so that's better. Not great, but better enough. All right, so we're going to put 0 here. We're going to put 1 here. We're going to, let's see, I'm going to do 2 and 3. This is just sort of a review in terms of how to build a histogram. 5, 6, and then out here is 7. Okay, and then we're going to build our histogram. So this will be 0. We'll go, how much do I need to go up? I got to go up to 6, right? So 1, 2, 3, 4, 5, and 6. And I know that for 0, let's see, I think I grabbed that right. I did. Perfect. For 0, there were 2. So for 0, again, I apologize for my drawing. For 1, there were 6. So I got to go way up here. Whoops. I got to go way up here to 6. And then way down there. For 2, there were 4. So over here and over here. For 3, there were 2. And then there was nothing for 4, 5, and 6. And then all of a sudden, out of nowhere, at 7, we end up with a value. Now, hopefully, at this point, you're looking at that going, Ripley, that's starting to smell like an outlier. Is that an outlier? Well, based on what it did to our mean, you'd probably be correct, and we'll come up with a way to figure that out as we get through these measures of variation here in just a second. Okay, so this is going to be the data that we're going to play with. Okay. Like I said, the range is the most rudimentary. I'm not even going to say fundamental because it's really just the simplest way to describe variation. I'm going to give you a piece of vocab right now that will plant a seed, because this is what we're really care about. Standard with an E. Goodness. It's called standard deviation. And I know for a fact that you guys have heard standard deviation mentioned probably 1,000 times in your lifetime. And you probably don't truly know what it means. All right, standard deviation. Well, I hear it when I hear people talk about IQs, and they say the mean is 100. I now know what that means, and the standard deviation is 15. What does that mean? Standard deviation. There's lots of ways to explain it, but I have found that the easiest way to explain standard deviation, it's simply the average distance. Average distance of the data values to the mean. So if I wanted to figure out what the standard deviation of this data set was, what I could do is I could figure out the distance from 0 to 1.8. From 0 to 1.8, from 1 to 1.8, from 1 to 1.8, etc., 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 2 to 1.8, 2 to 2, 3 to 1.8, 3 to 1.8, 7 to 1.8. Take all those differences, add them up, and divide by the number of data that I have. Okay? Now, unfortunately, it's not as simple as that. So, how do you find the standard deviation? You may ask, if it's not as simple as what I just described. Well, I'm going to show you the formula for it, but first we need just a little bit of notation. The first bit of notation is S. I don't know why it's blue, but let's stick with it because it's pretty. Excuse me. S is the sample standard deviation, and I get kind of lazy with this. It's excuse me, the sample standard deviation. Sigma looks like a 6 with a broken back. This is the population. Oops. This is the population standard deviation. Now, I want you to start noticing something here, and I'm going to write this down on the side. This is population standard deviation. In statistics, lowercase it usually implies sample. Lowercase Greek usually implies population. Remember back in the day when we did average, X bar was the sample mean and mu was the population mean. Same thing is true. Lowercase standard issue letters is sample, and lowercase Greek is population. Okay? Now, watch what we do here. And I'll explain why we do. I'm just going to take you through this just this one time because I want you to realize what's going on. All right? So first things first is I'm going to list the data. And I think there were 15 of them, right? So I'm going to go 0, 0, 1, 1, 1. How many were there? 1, 2, 3, 6, 4, 5, 6. There were 4 2s. 1, 2, 3, 4. There were 2 3s. And a 7. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15. Perfect. I'm going to write that down just for giggles. So this is n equals 15. All right, now we also knew from before, from over here, we know that the mean is 1.8. So what I'm going to do is, let's just write that down so we have it sitting up here. Mean equals 1.8. Now, I'm going to take x minus the mean. All right. Now you can think of this as the distance that isn't an absolute value. So we're actually going to get we're gonna get some negatives in here. So 0 minus 1.8 is negative 1.8, negative 1.8, negative 0.8, negative 0.8, negative 0.8. Let's see how many times. 6 times. Negative 0.8, negative 0.8. Negative 0.8. That's 6, right? 1, 2, 3, 4, 5, 6. And then 0.2, 0.2, 0.2, 0.2, 0.2, 1.2, 1.2, 1.2, and then what is that? 5.2? 5.2. Now, you may say, okay, these are sort of like distances, but they're not absolute values of distances. However, if at this point you're like, well, why don't we just take the average of these? Well, the problem with that is if I take the average of all of these, if I sum this up, and the way that you would see this is this capital sigma means add it all up. The sum of x minus x bar is always 0. So that doesn't make any sense, because when I go to find the standard deviation of this sample, I'm screwed. Now, let's think about this. If the sum of these is 0 always, regardless of what my data values are and what my mean is, that will always be true. You can sort of explore that if you want to. The way to get rid of the negatives in absence of the absolute value, which is called the absolute mean average, what we do is we're going to square it. So I'm going to take x minus x bar and I'm going to square this sucker, okay? So if I go, let's see, 1.8 squared, I'm going to get 3.24, 0.64, 0.64, 0.64, 0.64, 0.64, 0.64, 0.64, what's that, 0.04, 0.04, 0.04. Am I drifting here? No, I'm good. 0.04, 0.04, 1.44, 1.44, 1.44, and then 5.2 is going to be 27. That's a big one. 27.04. Now, your spidey sense may be tingling just a little bit here, and you're right to do so. What we just did, if you think about it, remember the units on this data were number of kids. So the units on all of these x's are number of kids. The units on the differences is also number of kids, because number of kids minus number of kids is going to be number of kids. The problem is, as soon as we square this, we end up in trouble because we've lost the units. All right, but we're not going to panic. What we need to do first is add all of this up, and just bear with me as I throw this in my calculator real quick. Whoops, 3.24 times 2 plus 0.64 times 6 plus 0.04 times 4, right? Times 4 plus 1.44 times 2 plus 27.04. So it's 3.24 and 6 and 4 minus 2 and booyakasha. I get 40.4. Hopefully that's the same. So 40.4. Okay? Now, don't freak out yet. Don't freak out yet. Okay? Because what we're going to do now is we're actually going to find S. And this is going to look really strange. And we'll think about this more critically in class. We'll talk more about this. Because remember, the vast majority of all of what we're doing here by hand is going to be done on your calculator. I'm not going to force you to do but maybe one of these by hand. So don't panic and say, Ripley, I'm going to screw this up. Don't worry about it. You'll get lots of practice. Now, what I'm going to do is I'm now going to take 40.4